When you're solving heap problems, what could be better than one heap? Well, sometimes two heaps is required to find the optimal solution. And this is the pattern we're going to be talking about now. It can commonly be applied when we're talking about medians. So if you forgot what a median is, basically if you took a set of numbers, to find the median is basically to find the middle value when those numbers are sorted. So for example, if we were given an array like this one and we wanted to find the median, well, the easiest way would be to take this array and sort it so it would look something like this. And then to find the median would be basically to go to the middle index. Since our array in this case is of odd length, we would just calculate the middle index and go to it. So in this case, our median would be 4. But maybe if we had an even number of values, then our middle index would actually be 2 different indices. So these two, and then to calculate the median of a even set of numbers, since there isn't a middle value, we basically take the 2 middle values, in this case 3 plus 4, and then divide that by 2. So our median in this case would be a decimal 3.5. And if you're given an unsorted input array, you can't really do much better than that. In the worst case, the time complexity of this solution, because we're sorting, is going to be big O of n log n, and you can't really do any better than that if the input is unsorted. Maybe if we were already given a sorted input, we could basically solve the problem in constant time, actually, because we would just have to get the middle indices and then, return the result. So it's all about sorting in this case. But what if we're actually given an even more complicated problem? What if instead of being given all the numbers up front, we're actually given a stream of values? So we're streaming values. So initially we only have the 4, but then we have 2 values. We have these 2, and then we basically keep getting values as time goes on. And of that stream of values, the values that we've seen so far, if we want to continuously find the median of those values, then what can we do? Well, to solve that problem where new values can be inserted into the set and we have to continuously get the median from that set, doing it the naive way that we kind of talked about with sorting is not going to be the most efficient, because suppose we're just given 1 value so far, finding the median is easy, but then we're given 2 values, finding the median is still pretty easy, but then we're given 3 values. At this point, we'd probably have to sort this and then find the middle number. And then as the set continuously grows, we initially had these 3 values, but now we inserted a new one. Now we already had these 3 sorted, so we don't necessarily have to sort all of these again, but we had these values. Now we're inserting a new value. Well, we probably don't want to just insert it at the end. We want to insert it in a sorted order. We want to maintain the sorted order of our set of values as we continuously add a new value. So to insert a new value in this case is going to be a big O of n time operation. But getting the median is going to be pretty easy, because when you already have a sorted array, getting the median from that is a constant time operation. This is not a terrible solution because our get median is pretty efficient, but as we continuously insert values, it's going to be expensive. I mean, what if we don't have to get the median very frequently? What if we're actually running insert a lot more? What if we have a really, really big set of values? Then this is not super efficient at all. If our set grows to a size of n, having to insert each value in sorted order would have made the total time complexity just of inserting n squared. Now, there's actually a solution that we can do it more efficiently, where doing the insertion is actually a log n operation, and getting the median is still a constant time operation. Now, how can we implement this? Well, you guessed it, using 2 heaps. So the idea is that we're going to have a couple heaps. One we're going to call the small heap because it's going to contain the smaller values of our set of values that we have so far. And we're also going to have a second heap for the large values. It's going to have the large half of the values that we have so far in our set. Now the small heap is going to be a max heap. Now the heap that has the smaller values is going to be a max heap, and the heap that has the larger values is going to be a min heap. That might sound counterintuitive at first, but bear with me, and by the end, this will make sense. So the idea here is that we're actually designing a class. We're designing a median finder class where we can arbitrarily insert new values into our median finder and we will arbitrarily get median from it. So the order that we do these operations could be random. We might insert 2 values and then we might calculate get median. We might insert 1 value, then calculate get median, then insert another and then get median and then another and then get median and keep going like that. It could be random, but we have to be able to handle all cases, all valid cases at the very least. Let's assume that we don't get median when we have no values inserted at all, just for simplicity, because that's an edge case. When we insert a single value, it doesn't really matter which one of these heaps we insert it into. So arbitrarily, what I'm going to do is just take the first value 4 and insert it into the small heap. So now if we call get median, it's a pretty simple thing to do because we just have a single element anyway, so we would just return 4. So these are just simple cases so far. Now let's insert a second value 7. So what we want these two heaps to represent is of the values we've added so far, so we have 4 and 7, we want half of the values to be in the small heap and we want half of the values to be in the large heap, and we want every value in the small heap to be less than or equal to every value in the large heap. So based on that criteria, you tell me, where should we insert this 7? Should we insert it here or should we insert it over here? Well, probably we should put it in the large heap, and that's exactly what we're going to do. So now if we want to get the median, we would first basically take the length of both of these heaps, and since we know the lengths of both of these heaps are exactly equal, that means we know for sure we have an even number of values total in our set. Because remember, the number of values in both of the heaps should be roughly equal. So at that point, we would take 4 and 7 from each of the heaps, add them together and divide by 2, and we would return, 11 divided by 2, that's going to be 5.5. So these are simple cases so far, but as we grow our set of values, you're going to see how we're going to start handling these cases. So next we want to add a 3. Well, which heap should we add this into? Well, just by looking at it, you can probably tell that we would want to add the 3 to the smaller heap. I mean, it's smaller than basically all of the values we have inserted so far, but how would you know that programmatically? Well, you would definitely know that we shouldn't put it in the large heap, because the large heap, it's going to have the greater half of values. And since it's a min heap, we're going to be able to get the minimum value from that heap in constant time. We're not popping, we're just reading what the value is, so we can do that in constant time. And we're going to see that 3 is smaller than the largest value in this heap. So probably it shouldn't go in that heap, it should go in the other heap. So that's what we would do. We would insert the 3 over here, but we kind of have a problem because the lengths of the heap are not equal at this point. But in this case, since we have an odd number of values, we can't really do anything about that. There's no way we can make the lengths of these two heaps equal. So we're just going to leave it as it is, because we know that the size of this heap is 2 and the size of this heap is 1. So as long as the difference of the lengths of the heap is at most 1, that's okay. But if we had, for example, 3 values in this heap and 1 value over here, then that definitely would not be okay. We would move one of the values. So this would be of size 2 and this would then be of size 2 again. And of course, if we had, 4 values here and 1 value here, that would also not be good. We would at the very least move one of the values to the other heap to get the difference to be less than or equal to 1. Now, I've been a bit misleading about one thing so far. When we take a new value and insert it into one of the heaps, we kind of already talked about multiple conditions that could happen. First of all, when we started and we had no values in either of the heaps, we just arbitrarily took that value and put it in the small heap, and it turned out that it worked in this example. And then when we had a second value, we saw that that value is greater than the previous value we inserted, so then we just went and put it in the other heap. But if that wasn't the case, we probably would have had to swap the values. If 7 instead was 2, we probably would have had to put the 2 over here and then moved the 4 to be in there from the heap. We'd have to move it to the other heap. And now that we're inserting a new value, 3, and both of the heaps are non-empty, we kind of have to compare what's values here, what values over there. Is this a big value? Is it a small value? So you can see that there's going to be a few conditionals that we'll have to write to know which heap to insert a value into. There's an easier way to do it. So in this case, The simplest way to do it is just to take every time we have a new value, just put it in the small heap every single time. Now, we don't know for sure that that's the correct thing to do, but we're going to start out by doing that. But after we perform that operation, we want to verify two things. We want to verify that all values in this heap are less than or equal to all values in that heap. What's an easy way we can do that? Well, we're just going to take the max value from this heap. So good thing this is a max heap. We're going to take the max value of our small values and make sure that that value, in this case is 3, is less than or equal to the smallest value in the large heap, which in this case is 7. Since that's confirmed, since this is the case, we don't have to do anything. At least we know all these values are less than or equal to these values, but we don't necessarily know that the sizes are equal. So we actually have to check that as well. We have to check the length of this heap, which is 2, and the length of this heap, which is 1. We have to make sure that the lengths don't differ by more than 1. If they did, for example, if this one was 3 and this one was 1, so this has extra values and this one has less values, then we would take a value from this heap and push it into this heap. How can we do that? Well, which value would we want to pop from here? Probably the largest value, right? We wouldn't want to pop a small value. And good thing this is a max heap, so we can do that in log n time. We can take the max value, pop it, and then push it into the other heap, and that is also a log n operation. If the opposite was the case, maybe we just had one value in this heap and we had 3 values in this heap, we would probably want to take a value from here and then push it over there. Since these are large values, these are small values, we would want to take the minimum value from this heap and then push it to the small heap. Good thing this is a min heap, so we can do that efficiently. So that's the easiest way to make sure that these heaps are basically following the properties that we have set for them. And now if we wanted to calculate the median, because we know that the heaps are roughly equal, these values have the small values, these values have the large values, how do we get the median at this point? Well, since we know this heap is larger, we know that the median is going to be in this heap because we technically haven't sorted all these values, but we have a sorted property. These are the values we've added so far. We want to get the middle value. Since we know the heaps are of uneven size, we know that these values are in the left heap and this value is in the right heap. We want the middle value. Well, good thing this is a max heap. We can get the maximum value in constant time because we're just reading it, we're not popping it. So when we get median here, we would just get 4. We'd get the max value from our max heap and then return it. Of course, if the heaps were like this and we had 4, 7 in the large heap and we just had 3 in the min heap, we would do the same thing. We'd take the minimum value from our large heap and then we would return this value. So you can see how these heaps make it easier for us to find the median. We've set them up intentionally in a way that they will easily allow us to find the median value continuously. Now let's look at the case where we have an even number of values by taking this 5 and inserting it. And I'm going to insert it in the way that I talked about. So we're arbitrarily going to put the 5 here. We're going to put it in the small heap. But now we see that the small heap has 3 values and the large heap has 1 value. So we want to pop from here. We're going to pop the largest value because this is a max heap. We're going to pop that 5 that we just inserted, and then we're going to insert it into the large heap. So now we put that value in the correct heap and their heaps are of equal size. So that's good. Now if we want to get the median, we actually have heaps that are of exactly the same size. So we have an even number of values. So how do we calculate the median then? Well, we're going to read the max value from our small heap. We want, let's say this is our set of values at this point in sorted order. These are the values in our left heap and these are the values in our right heap. We want to take the 2 middle values, add them together and divide by 2. Well, good thing from our max heap, we can get the max value in constant time. That's this 4. We can get the smallest value from our large heap in constant time. That's this 5. Add them together, divide by 2. We get 9 divided by 2. That's going to be 4.5. So we can do this pretty efficiently. The get median is always going to be a constant time operation because we're setting up the heaps in that way so that we can basically guarantee that. Now, lastly, let's just look what would happen if we took this 1 and added it. We're going to arbitrarily insert it into the small heap. It turns out that that's the correct thing to do because now we're going to read the largest value from here, which is 4, verify that 4 is less than or equal to the 5 over here, And since that's the case, that means we know that all these values are less than or equal to all these values. That's good. Now, lastly, let's check that the sizes are roughly equal. This is a length 3, this is a length 2, so the difference is 1, but that's okay. So the insertion is completed. Now, if we wanted to try getting the median, we would see that this has a length of 3, this has a length of 2, this has a length of 2. So if we want to get the median, it's probably in this heap, and we would take the max value from that. So 4 would be our median in this case. So you can see that when you set it up with heaps, rather than just keeping a single sorted array, we can get the insertion from a linear time operation, and we can get it to be a log time operation. So this is what the code for that would look like, at least in Python, but most of these ideas can be extended. So our constructor will basically initialize 2 heaps, just like I talked about, a small heap and a large heap. In Python, that's essentially an array, and then we can run heap operations using the heap class. But of course, this might be different in other languages. Now, the 2 operations that we're supporting are insert and get median. You can see the bulk of the work is in the insert operation. That's also the operation that runs in log n time, because when we get a value and we insert a number, we're arbitrarily going to push it to the max heap and only swap if needed. So we're going to take that value and insert it into the small heap. So this is that value. Now, the thing about Python, this isn't true for most languages, but Python does not have a max heap by default. So a way to get around that actually is when you're inserting a value to actually take that number and multiply it by -1. This will turn that heap into a max heap. You can apply this same technique in other languages if you want to, if that language doesn't support max heaps. Basically, if we were adding a value of 3 and 2, like these are our 2 values we're adding to our max heap, but this is actually implemented with a min heap, but we wanted to simulate what a max heap would do, we would take these numbers and actually multiply them by -1. So now we'd have -3 and -2. So now if we pop from the heap, we're going to end up popping the -3, which is what a max heap would have done. A max heap would have popped the 3 instead of the 2. So in this case, we're popping the -3, but since we know we multiplied the value by -1, we're going to have to multiply it by -1 when we pop from it again to counteract that effect. So when we pop from it, we'd get rid of the negative and we'd have a 3. So that's how we could simulate a max heap using a min heap. But moving on to the main concepts here, after we push to the max heap, we want to make sure that none of the properties of our 2 heaps have been violated. The first thing we want to check is that this value was inserted into the correct heap. How we can check that is first by making sure that both of the heaps are non-empty, because if one of the heaps is empty, then we can't really compare the 2 heaps. But if they're both non-empty, then we're going to take the root value from the max heap and the root value from the min heap and compare them. If it turns out that the largest value from our small heap is greater than the smallest value in our min heap, or a set of large values, this means that we violated the property where we want all values in the left side to be less than or equal to all values in the right side. So if we violated that, then we have to pop from the small heap and push to the large heap. We're popping from here and then pushing to the other one because by default, we know we always push to this one. So we'd pop from the small heap, multiply the value by -1. That's only required in Python because of the reasons I just talked about. And then we take that value and then push to the min heap. When we push to the min heap, we don't have to multiply by -1. So that will make sure that that sorted property is handled between our 2 heaps. But what if they are of uneven size? We haven't handled that yet. So that's the next thing that we would do. We would check if the length of one of our heaps is greater than the length of the other heap +1 though, because we know in some cases, if we have an odd number of values, then one of the heaps is always going to be greater than the other one. But is the difference greater than 1? That's what we're asking when we add +1 to the other heap. So if this is the case, then we'd obviously have to pop from this heap, which we're doing here, and then we'd have to push to the other heap, which we're doing here. Or maybe the opposite is true, where the other heap is larger. So we would check that with a second if case, and then do basically the same operation, pop from the heap with more elements, and then push to the heap with less elements. So one thing I'll say is that this is a relatively elegant way to write this code. This is probably not something you'd come up with just to arbitrarily push to one heap and then, handle the case like I did. And that's completely okay. The first time I tried solving this problem, I think I just had a ton of different conditionals. And that is completely valid and it works. It just turns out that that code can get messy. It can be hard for you to write. It can be hard for somebody to read. So I want to say that if you're trying to solve this problem and you write code that looks different than this, but as long as it works, that's completely okay. Because as long as you understand the idea behind two heaps, that we want the heaps to be of roughly even size. We want one of the heaps to have values that are less than or equal to the other heap. That's what's important. These concepts that we're talking about are important. If your code isn't perfectly elegant, that's okay. If you have a few extra lines of code, that's okay. The concepts is what you should be focusing on. Now, for getting the median, this is the easy part. This is the part which we can do in constant time. We're going to first check, do we have an odd number of values? In other words, is one of our heaps larger than the other? Because we know the heaps should be of equal size unless, of course, we have an odd number of values. So is the small heap larger than the other heap? If that's the case, we're just going to take the max value from that heap and return it. Of course, we're multiplying by -1, but that's only a Python thing. The other case is if the other heap is larger, then we take the value, the root value from that heap, the smallest value, and then return that. But if we have an even number of elements, then we know we actually have to calculate the average between two elements, the two middle values. So we would take the root value of this heap and the root value of that heap, add them together and divide by 2, and then return that. So admittedly, this might not be a pattern that you'd come up with on your own. Like if you had never heard about this pattern, you would probably not be able to solve problems requiring it. But as you practice it, and now that you've been introduced to it, it's definitely something that can come up in interviews, and having seen it before can definitely make a difference in being able to solve a problem optimally. But just seeing this pattern in action is not enough. I highly recommend practicing it for yourself, even if you have to practice, this problem that we just talked about. Now that you've seen a possible solution, try solving it on your own. Maybe come up with your own way to solve the insert function, even if it requires more code.